Hello, today we start a new topic. This is called the sweep paradigm. This is an important and interesting thing which is very specific to geometric algorithms. So what happens here is that some object, maybe a line or a ray, circle, rectangle, this sweeps through the plane. Okay. So some object like a line or a ray sweeps to the plane, and definitely it has infinitely many, even uncountably many positions, but at only some specific positions which should be finite for this to be an algorithm. So at some finitely many, I better say, finitely many positions, of the sweeping object, some events happen, something special happens. So, if we can handle these events, our problem is solved. Geometric problem is solved. So, this is the basic idea. Is solved. Okay. So, this is the basic idea, but unless I give you some example, this makes little sense. So, I start with a problem and specify a set of tricks. The problem is called the line segment intersection. Okay, so what does it deal with? So you are given n line segments. Let us name them L1, L2 up to Ln. Now these are line segments. This is important. You note that these are line segments, not lines. It's only finite. So each Li is specified by the two endpoints Pi and Qi. Okay. So each is a point and therefore contains an x coordinate and a y coordinate. Pi is pair xi comma yi. This is something like xi prime, x prime I, y prime I, something like that. Okay. So when I talk about line segment intersection, the question is, we want to find out whether a line like this and a line like this intersect. Intersect means if this is P1, this is Q1, this is P2, this is Q2, we say they intersect. On the other hand, if I have a situation like this is P1, this is Q1, and another line like this, P2, Q2, then although if I extend this line, it intersects this P1, Q1, I will say they do not intersect. Okay. So only from the beginning of a segment to the end of a segment, if there are any intersection point, I want to find out. So this is they intersect in this case, and in this case they do not intersect. Okay. So, and this is the intersection point which I want to output. So, given n-line segments, I want to find out all intersection points. Okay. So, my task is to compute all the intersection points. Okay. So an obvious algorithm is for all I, for all j, you find whether line Li and line Lj actually intersect. If so, you find that point of intersection and report. Okay. But there are actually n choose 2 pairs Li, Lj. Okay. And even if you compute the intersection of each Li with each Lj in constant time, this still requires theta n squared time. Okay, so this is basically an exhaustive search or naive algorithm, whatever you call. And indeed, in reality, the given line segments may have theta of n square points of intersection. If it so happens, then definitely this exhaustive search or the naive algorithm is optimal. You cannot do anything better than this. But if the number of intersections of these line segments is much smaller than theta n square, then this is definitely not a good algorithm. Okay, so let's say H is the actual number of intersections. If H is big theta of n square, then this is definitely the optimal algorithm. Nothing better you can do. If H is not so, we will do something, an output sensitive algorithm, whose running time will be big O of n plus H log n. Okay. So if H is small o of n square by log n, this algorithm wins over this exhaustive search algorithm. Okay. So this is better. Moreover, if I look at this exhaustive search algorithm, its space requirement is actually very good, just O1. So here I will make I have to use some more space, but let us say that we will not use more than big O of n space. Okay. So with these two things in mind, running time will be something like this and space requirement will be something like this. I will give you a line sweep algorithm. For solving this problem. This is a line sweep algorithm. This algorithm requires the input lines to be in general position. So L1 through Ln should be in general position. And that means, in this context, 1, no 2x coordinates of the endpoints of the segments and also the intersection points are same, are the same. This is a vital requirement. A more vital requirement is that no Li is vertical. Third, we may also assume, but it's not so much necessary, that no two Li, Lj are parallel. This is not so much needed, but anyway, we can make this assumption. Now, what happens in this algorithm, this line sweep algorithm, a vertical line sweeps from x equal to minus infinity to x equal to plus infinity. Okay. And definitely from minus infinity to plus infinity, there are infinitely many positions of the line. But let us say, did I mention it is P and Q? Yeah, P is the left endpoint, Q is the right endpoint. Okay, it's having the smaller x coordinate, this is having the larger x coordinate. Since we assume that no lines are vertical, this x coordinate is always smaller than this x coordinate. Okay. So, definitely, the sweeping line, let us call it L. This will have infinitely many positions. We simply cannot evaluate all of these positions. But if I consider, let's say, start to be this x coordinate, minimum of x coordinate of P1, x coordinate of P2 and so on up to x coordinate of Pn, and if I consider end is the maximum of the x coordinate of Q1, x coordinate of Q2 and so on up to x coordinate of Qn, then you can see that to the left of start, nothing significant happens, nothing relevant happens. Likewise, when the sweep line moves past this x coordinate, then also nothing relevant happens. So we will only consider L moving from this x coordinate start to the x coordinate called end. Still, there are uncountably many positions of L, okay, from start to end. So most of these positions are not very interesting, but only at some finite number of positions between start and end, some finite number of positions of L, events will happen. And in this context, we will have three types of events. One is called enter segment. Second one is called leave segment. And third one is called intersection. We will handle these three events, okay. So there will be n intersegment events because there are n points, n line segments, and there are n line segments, so there are again n, and intersection, that would be h. So the total number of events will be 2n plus h. If I am able to handle each of this event in big O of log n time, then I get the desired running time of big O of n plus h whole times log n. Okay. So to handle each n O log n time. Moreover, as I mentioned, the total space requirement, I do never want to exceed big O of n. Okay. So, how does it work? So, to understand it, let me first introduce a picture. Okay. Make it little small. Switch to this mode. Okay. So, these are my given line segments, and this vertical line, which is shown in red, is sweeping from minus infinity to plus infinity. And you can see that this point, this is basically start is somewhere like here, this x coordinate. So, start is somewhere here. And end is somewhere here. So, monitor the sweep line going from start to end. Okay. So, we will maintain several things. Okay. Two data structures actually we will maintain. One is called the sweep line information. So what does it mean? For any position of the sweep line, as in this case, you can see for this position of this sweep line, this is intersecting with this, and this. So these are the lines shown in bold. And let us call these lines active. I mean line segments active. So we have 1, 2, 3, 4, 5, 6 active line segments. And 1, 2, 3, 4. Some segments are not active, so these are shown by thin lines. Okay. So the sweep line, whatever data structure we use, but we maintain this information against in S, the set of all active lines, but we will keep them sorted with respect to their y coordinates. May be sorted from top to bottom. Okay. Now, okay, so it's a set of all active lines sorted from top to bottom, but S will not store the y coordinates of the intersection of the sweep line L with the active lines. Okay, actually only their relative position with respect to the sweep line L is important. So I will maintain this followed by this, followed by this, followed by this, followed by this, followed by this. Now why do I not maintain y coordinates? Because you see, before this red position, slightly before this, all the y coordinates were different. And when the sweep line moves slightly, there again all the y coordinates change. So we do not want to maintain this y coordinate. It suffices to know that they are relative position. So this line first, then this line, then this line, then this line, then this line, and then this line. Moreover, this picture shows a general position where a slight movement of this sweep line to the left or right does not change this relative position. Okay, this relative position is here exactly what it is. Here it is exactly as it is. Here also it remains the same. Okay. So the sweep line, we will not store y coordinates, we will store their relative positions. Okay. Now the question is, when does this relative position change? Okay. So the change when a new segment is entered becomes active. Okay. Or when the sweep line moves past the right endpoint of a segment so that this no longer remains active, or when the sweep line encounters an intersection point, so after that their relative position is just swapped. This now becomes this. Okay. So, this is the only situation: enter segment, leave segment, and intersection point when something interesting or relevant happens. I need to make some change to S. Okay. In addition to this, I will maintain an event queue. Okay, since I have used Q for a different purpose, let us call it E. This will store segment endpoints to the right of the current position of L, and it will also show store, okay, let us say Li and Lj are consecutive in S. The current position, Li and Lj are consecutive. Maybe Lj is coming just after Li in the sweep line information, and I will denote by this notation intersection Li Lj, something like this, or Li intersection Lj, to be the x coordinate of the intersection point. This is just a notation. Okay. Now, if Li and Lj are consecutive in S and have an intersection to the right of the current position of L, then the event queue will store this E. Okay, so let me write it down. So if this is the condition, one condition, they are consecutive in S and this intersection point is to the right of L, then I will store this X coordinate. So this event queue E will store X coordinates only. Okay. Moreover, it should store additional information like this endpoint belongs to, if it is an event like this, so this endpoint belongs to which line segment, and whether it is the left endpoint or the right endpoint. Likewise, if an X coordinate is stored like this, then it will have to store it is the intersection of which I and J it will have to store. But Y coordinates are never stored. Okay. This will give a problem. We will work around this problem later. Okay. Okay. So now, once we have our data structures conceptually ready, S will store only this thing in sorted order from top to bottom, and Y and E will store the future endpoints that the line will encounter and some of the future intersection points. Let us look at this position. This and this intersect, and this intersection point is to the right of the current position of the sweep line. So, this will be stored in the event queue at this position of the sweep line. You see that this and this and this, they also intersect. But this and this and this are not consecutive on the sweep line. Therefore, these intersection points will not be stored at this position of the sweep line. They will be inserted later when time comes. Okay. For example, after the sweep line crosses this intersection point, then this and this become consecutive, then this will be inserted. Okay. Fine. So, the event queue will store future endpoints and intersection points, if any, of consecutive lines. Okay. If anything is there, if they intersect at all, and that intersection point is to the right. Good. Now, let us see one by one how each event is handled. So once again, let me introduce a picture. This picture, oops, okay, fine, no problem. Anyway, fine. So this picture shows an enter segment event. Okay. So at this point, L1, L2, L3, L6, L5, L7 is, so let me write down. So at this point, S contains, just before this enter segment event, S contains this sorted list L1, no, it's not L1, L2 first, then L1, then L3, then L6, then L5, and finally L7. Okay. Now, a new segment is going to become active and stay active for some time in the future. That is L4. Okay. So, at this point, let us see. I'm going to use the mouse. It's better readable. So they intersect, but this intersection point is to the left of this. So this will not be stored in the event queue. But this and this intersect. So this intersection point is to the right of the sweep line. So this will be stored in the event queue. This will not be stored. This will be stored. Okay. These and this will be stored. But from now on, this L4 will remain active for some more time. Okay. So I have to somehow insert L4 between L3 and L6. So I have to insert L4 somewhere here. Okay. Now I will look at L3 and L4. Were they intersecting? Yeah, they were intersecting earlier. L3 and L6, sorry. L3 and L6 are intersecting. So this was in the event queue because L3 and L6 were consecutive on the sweep line. So this was in the event queue, this point. But now since the introduction of L4 makes L3 and L6 non-consecutive, I will delete this from the event queue. Okay. So the sweep line information changes only this way. Okay. Just insert L4 between L3 and L6. And what are the changes I make to E? Delete this intersection of L3, L6 because they are no longer adjacent, consecutive on the sweep line. But since L4 is introduced, L3, L4 and L4, L6 I have to check. So L3, L4, let us see. If L3 and L4 are like this, L3 and L4 do not intersect actually. But L4 and L6, they do intersect, and that intersection point is to the right of the segment, sweep line. Therefore, I will introduce this in the event queue. Okay, so L3 and L4 now do not intersect. So I will do nothing. But L4 and L6, which have now become consecutive, they have an intersection point. So insert intersection of L4 and L6. Okay. So I am deleting this. Of course, I could have kept it, but I am deleting this in order to ensure that my event queue never uses more than big O of n space. Okay. This deletion is necessitated by the space requirement, big O of n. Otherwise, this deletion is not really very necessary. Okay, with respect to the running time. Okay. So this is how I handle one enter segment event. Insert one thing here somewhere in the appropriate position. Before that, I find out. Okay, so of course, now there is a question which I will answer at the end. Since we are not maintaining any y coordinate, how shall I locate L4? Okay, in this list. I will answer this question later because we are not maintaining any y coordinate anywhere. Okay, so I will see how I will get around this problem later. Okay, so now let us see how we can handle a leave segment event. Okay, so another picture. Open, make it little smaller, then I switch to pen mode. Okay, so now let us see what happens here. Just before leaving this L1, which segments were active? In fact, all of this. Okay. So S was something like L2, L3, L1, L4. Okay, let me write. Before this leaf segment, the relative position was L2, L1, L2, L1, no. L3 was there. Sorry. L3 was there, so it should be L2, L3, then L1, L4, L1, L4, L6, L5, L7. Okay. So, now the sweep line is going to leave this segment L1. So, after this point, L1 will no longer become active. So, the sweep line information, I remove this L1 from the sweep line in this data structure S. Okay. And what changes I will do to the event queue? Okay, so one thing is clear. L1, the role of L1 is now over. So it's not possible that L1 has an intersection with L3 to the right. Likewise, it's not possible that L1 has an intersection with L4 to the right of the current position of the sweep line. So I do not need to worry about these intersections. But the removal of L1 now makes L3 and L4 adjacent on sweep line. So if they intersect and intersect to the right of the current position of the sweep line, I have to add this intersection point. So, but in this example, L3 and L4 do not intersect. If these are a bit longer and they did intersect, I have to insert L3, the intersection point of L3 and L4, x coordinate of that point to the event queue. Okay. But this is important, L3, L4 now are adjacent. So if they intersect and to the right of the current position, then I have to intersect. But here they do not intersect. So no insertion in the event queue E. Okay, so the next thing is, how do I handle an intersection point event? So again, let me explain this using a picture. Okay, make it a little smaller and then go to this. Okay, so now let us think of a situation like this. Okay. L1 is no longer active just before coming here, but L2 was active, L3 was active, L4, L6. So before this intersection point event, sweep line stores this sequence. L1 is not active, L2 is the topmost, then I have L3. Before the intersection, I have L4, L6, L5, L7. First of all, since this is an intersection point event, I have found an intersection point, so report. This is between L4 and L6. Then after this intersection, what will happen is that they will simply swap position. So L6 will come earlier, L4 will go later. Okay. So their position is just swapped in the sweep line information. This makes some other changes in the event queue. We will find out earlier these were adjacent L3, L4. So we will look at this intersection point if it is residing in E and intersection of L6 and L5. L6 and L5. If they exist in the event queue, I will delete them from the event queue because L3, L4 are no longer adjacent on the sweep line. L4 and L6 are no longer adjacent on the sweep line. So, to be deleted, if at all in the if no such point exists, it's okay. Now I have to, but this swap now have made L3 and L6 adjacent. So we have to look at L3, L6, and now L4 and L5 have become adjacent. So I have to look at L4 and L5. So let us look at this. L3 and L6. Actually in this case, yes. L3 and L6. So they are now adjacent and they intersect. But L4 and L5 do not intersect. So this I do not have to insert. So insert in E if appropriate. Okay. So this is how I handle the intersection point event, each intersection point event. Okay. In short, the algorithm can be written like this. This is a pseudocode. Let us see the pseudocode. Okay. Little bit up. Okay. Fine. So let us see how this works. So we have two things. Okay, I will use a mouse pointer. We have two things. E, the event queue. So I will initialize this to the 2n endpoints of the AN line segments, P1 through Pn, Q1 through Qn, in sorted order. Okay. I will never allow the sweep line to come back. It will always move right, and therefore I will process the events in the increasing order of x coordinates. So this P1 through Pn and Q1 through Qn should be kept in sorted order. Initially there is S is sweep line information. This is empty. This essentially indicates the position of S to the left of the start x coordinate. Okay. Then as long as E is not empty, keep on doing this. Handle the event. So pick up the next event, that is the event with the smallest x coordinate from E. Okay. Now look at this event queue store the information whether it is the left endpoint or the right endpoint, or it is an intersection point. Based upon that, you know what kind of event it is going to be. So if it is an intersegment event, okay, suppose that the left endpoint of Li has triggered this event. So insert Li in the appropriate position of S. Okay. I will tell how this appropriate position can be calculated in O log n time, big O of log n time. Now, after this insertion, you will look at the immediate predecessor of Li. Li is the new segment that is introduced, and Lt, the immediate successor of Li in S. Okay, they may be non-existent. So, I assume that they are both existent, but they may be non-existent. If they are non-existent, then do not do these things, whichever is non-existent. The point is that earlier Ls and Lt were adjacent. So, if their intersection point exists and lies to the right of L, delete it. But now, Li and Ls and Li and Lt, Ls and Li, Li and Lt, they have become adjacent. So, if their intersection points exist and lie to the right of L, insert. Okay. Now, this is how intersegment is handled. Leaf segment is handled this way. Okay, let's say the right endpoint of Li has triggered this event. So, let Ls be the immediate predecessor of Li just before this leaf segment, and Lt the immediate successor of Li in S. Delete Li from S, and now Ls and Lt are exposed as adjacent. So, if their intersection point exists and lies to the right of L, insert in the event queue. Okay. Finally, the intersection point, this is the most complicated. Suppose that the intersection of Li and Lj has triggered this event. So, simply report it. I have found an intersection point, and let Ls be the immediate predecessor of Li, this, and Lt follows Lj. Okay. Then you compute this LC and find out this Ls and Lt. Okay. Earlier Ls and Li, okay, interchange Li and Lj. Okay, in S, exchange their positions. Earlier Ls was adjacent to Li. So, their intersection point may be residing in the event queue. If so, delete. Earlier Lt and Lj were adjacent. So, if their intersection point was residing in E, delete. But now, we look at L. Because Li and Lj are interchanged, so Ls and Lj have become adjacent in S. So, if they have an intersection point to the right of the current position of L, insert it. Likewise, the intersection point of Li with Lt. Okay. So, this is how this works. How each event is handled. Now, let us, okay. Maybe once again I go to this. So, let us see what we require in S. What should it support? Arbitrary insertion. Okay, anywhere. Right. Likewise, arbitrary deletion. Okay. And swapping to consecutive elements, line segments. Okay. These three things S should support. On the other hand, E should support what changes you do, delete, insert. Moreover, at the beginning of each thing, you are choosing the element with smallest x coordinate. And after choosing, of course, you are deleting it. Okay. Pick up the next event and delete it from E. It's not written in this explicitly. So, at this point, I require delete min. Extract min or whatever. Not necessarily min. You read it and then delete it. Whereas, if you look at this point, These are inserts and deletes, deletes and inserts, inserts. But these are not at any specific position. These are arbitrary insert and arbitrary delete. Okay. Moreover, I need the x coordinates in the increasing, in the ascending order. Okay. S also has something to do with keeping the lines in ascending order. Okay, from top to bottom, active lines. So, because this involves arbitrary insert and arbitrary delete, which are difficult operations in a queue, priority queue or a heap. Okay, this is arbitrary insert and arbitrary delete is difficult. Okay, delete means fine, and insert at the end is also fine, but this is arbitrary. You have to find out that those elements in the heap array and then delete. So that search does not have any easy way with a priority queue prepared from a binary heap. Okay. But this also some kind of sorting, arbitrary insert, arbitrary deletion and swapping. So all these requirements are satisfied if we implement S and E as height balanced binary search trees. Like AVL or red-black trees. If we do so, let us see that each event can be handled in big O of log n time. Okay. So first of all, S at any point of time, this is a set of active line segments. So it does not contain at any point of time something more than n nodes, n nodes. Okay. In particular, at all points of time, the size of S, that is the number of nodes in the height balanced binary search tree, remains less than equal to n. And what is the maximum possible size of the event queue? This is less than equal to 2n endpoints plus, I am not storing all intersection points, I am storing intersection points of only consecutive active lines. Okay. So there can be at most n active lines at any point, and therefore this stores at most n minus 1 intersection points, which is 3n minus 1. So this is the upper limit. So the space complexity is big O of n. And each operation, initially you have to insert these events to an empty binary search tree, height balanced. Okay. And then you will handle how many events? N entered segment events, N leaf segment events, and H intersection point events. Okay. So, each insertion, deletion, each of these works, swapping, finding predecessor, finding successor, all this stuff can be done in big O of log n time if you maintain the height to big O of log n. Okay. So, eventually with a height balanced binary tree, we therefore this is space and we have big O of initially 2n inserts, then you handle 2n leaf or entire leaf segment events plus h intersection point events. Each can be done in log n time, which is same as big O of n plus h whole times log n. Okay. So that's how this algorithm works. Now I answer the last question attached to this. Let us think about E. This is a height balanced binary search tree, and I want to insert an intersection point in E, or for that matter it can be S, and I want to insert a new segment to S. Okay, but neither S nor E maintains any y coordinate. So how do I insert? So this is the last question. Okay. So how to insert? In absence of stored y coordinates. Okay, so let's say this is the tree, height balance tree, something like this. Okay. And these are all x coordinates and other things you have stored, but no y coordinate. And suppose now I want to insert some new thing. Okay. But it stores sufficient information about which line it is, blah blah blah. If it is an intersection point event, it is the intersection of which thing. So when I insert something, some event, let's say this is an event tree. This is the event. Similar thing holds for the sweep line information. I want to insert, let's say, some event. Okay. Some event. Some. Okay. Okay. Actually, this is a insert intersection of some Lij. Okay. So now I know the y coordinate of this, and this event, whatever is stored, it stores sufficient information. Okay. To find out at the given x coordinate of L where the event is happening, at this x coordinate, what is the y coordinate for this event? So it's not stored, but enough information is stored so that this y coordinate is computed at the given x coordinate. Now based upon that, now compare this y coordinate with this y coordinate. Maybe you come here. Okay. Once again you compute the corresponding y coordinate here. Okay. Compare with this. Maybe this time it goes here. Then once again you compute. Let's say you want to go here. Okay. So now this is empty. So create a new node and make it the child. So how do I insert in absence of stored coordinates? So the answer is compute only the y coordinates compared in the tree. Okay, compute only the y coordinates compared in the tree. Compared in the tree, yeah, only the y coordinates. So you, on the insertion path, you compute this. Okay. So since this path is no bigger than big O of log n in length, okay, and these y coordinates from the stored information can be computed, each can be computed in constant time. So you do not need to store y coordinates. Compute when necessary. Okay. So again, big O of log n overhead. But that is fine. Okay. Because each computation can be done in big O of one time. Okay. Okay, so that is a particular genre of algorithms which you have never seen earlier, sweep paradigm. So let me stop here. In the next lecture, I will give you another sweep algorithm. This time a line will not sweep, but a ray will sweep for 360 degrees. And that will solve another problem. Okay. So, bye.